Hey everyone, and welcome. Today we're going to add a real specialist tool to your calculus toolkit. It's called the ratio test, and honestly, it's designed to crack some of the absolute trickiest infinite series you'll ever face. So let's dive right in. Okay, so picture this. You run into a series that looks like this one. It's got factorials, it's got powers, and a lot of your standard tools, like the integral test, are just not going to be very practical here. It looks pretty intimidating, right? So the big question is, how on earth do we figure out if this monster actually adds up to a finite number?
Well, this is where our new specialist tool comes into play. The ratio test is built on this really brilliant idea. It checks if way out at the end of the series, the terms start acting like a simple geometric series. If the ratio between terms gets really small, the series converges. If it stays big, it diverges. At its heart, it's that simple.
And here's the machine itself. The formula looks pretty simple, and that's the beauty of it. All we're doing is creating this value, we'll call it L, by taking the limit of the absolute value of the next term divided by the current term. This one little number, L, is going to tell us everything we need to know.
Using it is just a straightforward three-step process. First, you just write out the ratio, literally plug your series into that formula. Step 2, and this is where the real work happens, you use your algebra skills to simplify that fraction down as much as you possibly can. And finally, you take the limit as n goes off to infinity, and that's it. So once you've calculated your L, the test gives you one of three really clear verdicts. This is what makes it so powerful. Well, most of the time.
Think of this as the instruction manual for the test. If your L is less than 1, the series converges absolutely. That's a rock-solid guarantee. If L is bigger than 1 or even infinite, the series diverges, no question. And if L lands exactly on 1, well, that's the one inconclusive case we're going to talk about in a bit.
All right, enough theory. Let's get our hands dirty and put this tool to work on the exact kind of problem it was built for, a series that's loaded with factorials. Here is our first challenge, the sum of n cubed over n factorial. Let's fire up the ratio test and see what it tells us. So first things first, we set up our ratio. We have the n plus 1 term on the left, and we multiply it by the reciprocal of the original term. Yeah, it looks like a mess right now, but you gotta trust the process.
Now here is the absolute key, the pro tip that makes these problems solvable. You've got to simplify the factorials first. Just remember that n plus 1 factorial is really just n plus 1 times n factorial. This little algebra trick is what lets the n factorial on the top and the bottom cancel out beautifully.
And look at that. After we cancel out those factorials and clean things up a bit, that huge, complicated fraction boils down to this much friendlier expression. So much easier to work with, right?
Now for the final step. What happens as n goes to infinity? Well, the polynomial on the bottom has a higher degree than the one on top, which means as n gets enormous, the whole fraction just gets squashed down to 0. So our L is 0.
We take that result, we go back to our rule book. L equals 0, which is definitely less than 1, so our conclusion is clear and super confident. The series converges absolutely. Problem solved. Okay, let's try another one. The ratio test isn't just for factorials. It's also an absolute superstar when you're dealing with exponential terms, especially when they're mixed up with alternating signs.
All right, this one looks even more wild. We've got powers all over the place, an alternating term, but don't worry. We just need to follow our three-step process, and it'll all work out. So after we set up that big old fraction, a really great strategy is to group the similar terms together. See, we put the powers of 9 together, the powers of -2 together, and the n terms together. And notice, those absolute value bars are super helpful. They make the negative signs totally irrelevant for our calculation.
Now we can just look at what each little group does as n gets huge. The 9s simplify to just 9. The powers of -2 simplify down to an absolute value of 1 over -2, which is just 1/2. And that last part, n over n plus 1, that heads towards 1. So what do we have? 9 times 1/2 times 1, which gives us an L of 4.5.
Back to our user manual one more time. L is 4.5, which is clearly bigger than 1. And that means our conclusion is simple. This series diverges. It does not add up to a finite number.
Now listen up, because this is important. Every specialized tool has its limits, and you absolutely have to know what they are. So let's talk about the single most important warning label on the ratio test. What happens when L equals 1? When L equals 1, the test fails. It just gives up. It tells you absolutely nothing.
And this happens a lot with series that are just simple fractions of polynomials, like the famous harmonic series 1 over n, or the piece series 1 over n squared. For these guys, the ratio test is pretty much useless. It's the wrong tool for the job.
So what do you do then? First, you don't panic. You just calmly put the ratio test back in your toolkit and you pick up a different tool. I mean, this is exactly why you learn so many different tests. Things like the comparison tests or the integral test are often the perfect choice when the ratio test just shrugs its shoulders.
And there you have it, the ratio test. It's a precision instrument perfect for tackling those tricky series with factorials and exponentials. It's powerful, it's decisive, and now you know exactly when to use it and, just as importantly, when not to use it. So the only question left is, what series are you going to test first?